In this video I am studying the noise in 22 ohm resistors. I have a resistor from here to here, DC blocking with 22 nanofarad polypropylene capacitors that I consider noise free. Then I can feed a DC current through these 22 microhenry inductors, through the resistor and then to ground here, and with a decoupling capacitor on the input, so I don't introduce any noise this way. I look first at this resistor. It's a 0.25 watt metal film resistor. There is no attenuation here, so I have the full signal. But 22 ohms reduces the power a little bit, so the level I have on the spectrum analyzer is 5.5 dBm. I have set 100 dB attenuation. That is to present 50 ohms here, to get 70 ohms out here. And then I establish the noise floor and check it. It shows now 0 to within 0.02 dB. The noise floor shifts a little bit, but the noise figure shouldn't change significantly with this modest impedance change. I have now set the attenuation to 0. The signal level I see is 5.45 dBm, and then the noise floor I can observe is 0.18 dB. So it's a very small increase of the noise. I now send about 230 or 250 milliamps of DC through the resistor, and it's not obvious at what point in time that happened, so I make a timestamp here by removing and putting back a connector. So I know for sure that the reading I take is with the current present. I have set the attenuator to 100 dB. That's in order to present 50 ohms to the input here, which will give 72 ohms at the output here. That will shift the noise floor a little bit, because the noise changes with the impedance for the low noise amplifier. But the noise figure shouldn't change much, so I don't take that into account. The noise floor I see now after changing the calibration is 0.003, so that's very close to 0. And now I turn on the signal by putting this to 0 and this one also to 0. Well, I didn't change that. And I see a very small increase on the noise floor. Very small indeed. So I have to wait a little and then I can read it out. Well, the signal level is 5.45, plus 5.45 dBm here. And the noise floor is 0.11 dB. So it's a very small increase. Now I switch on this power supply to send 250 milliamps through the resistor. It didn't make a visible change here, so I just click on the attenuator to get a timestamp so I know from where to measure. And now with current through the resistor, I see 0.16 dB. Hardly significant. My system is not good enough to see the noise in metal film resistors. And that is fine. I can use them wherever needed without any precautions. This is a 1/4 watt carbon film resistor. There is no attenuation and the noise floor is 0.11 dB. I switch this on to supply 250 milliamps of DC and make a mark on the curve so I know from where to measure. So I look here, and now the level is 0.18, so there is a small increase. This is a carbon composite resistor. I'm running it without any attenuation here, and of course the power has been the same for all the resistors. Resistors are 22 ohms and not different much. The noise level is 2.7 dB, so this contributes a significant amount of noise. I now add 250 milliamps of DC, and I don't see that, so I make a mark here so I can look at the noise level with current. And now it goes up. Presumably the resistor is getting warmer because of heating. So I switch off the DC current again, and I could see the transient here. And now we can see the noise is going down again. So the noisy component of the DC current does not modulate, but the increased temperature makes the resistor more noisy. This is what I found. Only the carbon composite resistor has a measurable noise contribution. It is at minus 193 dBc per hertz. The other ones are not significantly above the level of the system, so they are to regard as noise-free. Also the carbon film, which is maybe a little bit surprising.